Now we take the situation whereby we are not so close to the Earth. Here is the Earth itself. Of course, you can also replace that by the Sun if you want to. And this is increasing value of r. The distance between here and this object M equals r. I now know that there is a gravitational force on this object, Newton's universal law of gravity, and that gravitational force equals minus m Earth, g, divided by this r squared, r roof. So this is a vectorial notation. Since it is really one-dimensional, we would, just like we did there, we would delete the arrow and we would delete the unit vector in the positive r direction. And so we would simply write it this way. The gravitational potential energy we derived last time equals minus m Earth g divided by r. Notice here is r and here is r squared. And if you plot that, then the plot goes sort of like this. This is r. This is increasing potential energy. All these values here are negative. And you get a curve which is sort of like this. This is proportional to 1 over r. Now, of course, if the Earth had a radius which is this big, then, of course, this curve does not exist. It stops right here. If I move from point A to point B with a mass m in my hand, notice that the gravitational potential energy increases. I have to do positive work. There's no difference. If I go from A to another point, B prime, which is closer to the Earth, notice that the gravitational potential energy decreases. I do negative work. If I do positive work, gravity is doing negative work. If I do negative work, gravity is doing positive work. Right here near Earth, where this 1 over r curve hits the Earth, that is, of course, exactly that line. That dependence on y is exactly the same as the dependence on r, and then you can simplify matters when you're near Earth, when the gravitational acceleration doesn't change, you get a linear relation. But that's only an exceptional case when you don't move very far. The gravitational force is in the direction opposite the increasing potential energy. Notice that when I'm here, the gravitational force is in this direction. Increasing potential energy is this way, the force is in this way. When I'm here, gravitational potential energy increases in this way, the gravitational force is in this direction. When I'm here, the gravitational potential energy increases in this direction, the gravitational force is in this direction. When I'm here, the gravitational potential energy increases in this direction, the gravitational force is in this direction. The force is always in the opposite direction than the increasing value of the potential energy. If I release an object at 0 speed, it therefore will always move towards a lower potential energy, because the force will drive it to lower potential energy.